Hello everyone. Thanks for being here as the last talk in this session. My name is Jiechen. Today I'm happy to present in front of you with a great lake view about the SmartNIC-enabled live migration work. This work started in 2021. It's a long project and it involves many discussions around research prototypes, like demo to Microsoft Azure people, and also discussions on deployment. This is a joint work with University of Toronto and Microsoft. One sentence to summarize this work. This is the system architecture approach that achieves up to 17 times faster, much more reliable live migration with less than 1% SmartNIC area overhead. As you know, since a server is running for years, it may need various maintenance tasks for reliability, performance, load balancing, and security. Users may be affected on that server during maintenance. Resource interference can happen, and software updates may need seconds or minutes, while hardware updates may even cause service interruption. Our paper focused on a critical feature in more modern clouds, live migration. Live migration moves the states of VMs while the VM keeps running. So here we show an overview of a pre-copy live migration protocol. Say we have two hosts, source and destination. Initially, the VM is running on the source, and then live migration starts, where the VM is still running on the host, but it starts sending states to the destination host. With several seconds of blackout time, after that, the VM is running now on the destination host, but it may keep sending some extra states until the live migration finishes. And now we have the same VM running robustly and successfully on the destination host. Enabling live migration can help improve 50% availability, according to a study from Microsoft Azure. It helps for scenarios such as load balancing, power management, software hardware maintenance. The problem that this paper targets is that we have found live migration feature is missing for some new VM type, storage optimized VMs, for example. The screenshots here have explicitly says the feature is missing on GCP and Microsoft Azure. The goal of this paper is to answer the question, can the new VM type enjoy the live migration benefits? Before diving more details into our findings, I'd like to introduce the system architecture of the new VM type, storage optimized VMs. The figure on the left shows the legacy hypervisor managed architecture, where the host hypervisor software manages access to local storage. Storage optimized VMs, as shown on the right, bypasses the host hypervisor, mapping NVMe SSDs directly to the VMs. This system architecture shift improves I/O performance. However, the hypervisor cannot mediate disk access, so there is no consistency tracking during live migration. So if you do want to do live migration, you have to revert back to enable live migration using the legacy system architecture, where the live migration is supported in the hypervisor. So if we revert back, what can we do? The first question we answer is that live migration is just sequential data copies from one node to another over the network. Why it could be slow? The first thing we found is that live migration of a storage optimized VM is actually bounded by the data migration of the local disk. As shown here, it takes most of the live migration time, and that's because of the software overhead running disk migration. And if we add user workload, say we run random reads and random writes in the VM, we can see the disk migration becomes even slower. The reason is high consistency overhead, because some of the writes from the users has to be updated to the destination host. And those updates slows down the migration. Note that in this experiment, we run reads and writes both at 100 megabytes per second. If we run reads and writes at 200 megabytes per second, the disk migration is going to take 2 hours. And that's because of even higher consistency overhead, which saturates our 100G network. So the answer to the first question, why slow, is because of the software overhead and consistency overhead. The next question is, because line migration doesn't happen really that often, right? So why is still costly? It has something to do with the allocation strategy. We need to have a portion of resource to do line migration on the host CPU. The allocation could be on demand, only giving line migration some resource when it actually happens. But this is not doable because all cores are usually sold to users. And the remaining cores are used to run hypervisor. So there's often no core left when line migration is needed. If you're forced to deallocate resources from hypervisor or user, users won't be happy. So we must statically provision line migration resources. However, even for an infrequent line migration job, this static provision would make you lose revenue of thousands of dollars per core per year. And we found that to migrate each disk, there will be 6 to 10 cores needed. And often those nodes will have more than 10 disks on the local bus. So the answer to the second question, why costly, is due to we must statically provision the resources for line migration. So here is the system architecture comparing the host control line migration as our baseline versus our proposed work Pyrocumulus. As you can see, what we propose is to offload the line migration part down to the SmartNIC hardware. In terms of line migration cost, we can reduce the cost because even though we do statically provisioning, we only provision a little bit hardware resource on the FPGA SmartNIC to do line migration. And according to the paper in NSDI 2018, every server, at least in Microsoft Azure, have the FPGA SmartNIC deployed already. In terms of line migration time, we can also reduce the time because of the simplified data plane, which I will introduce next. So here's the server architecture, where the VM and the hypervisor is running on the CPU. And the VM could read data from a local SSD. And supposedly the line migration is initially on the hypervisor. And when it do line migration, it fetch data from local SSD and send it out to the network. In the meantime, the VM might write some new data on some blocks of the local SSD. And this inconsistency maintenance can burn a lot of CPU cores, which leads to high CPU overhead. The overhead makes the line migration slow and costly due to software overheads, consistency overhead, and on-CPU static provisioning. With the simplified data path we designed, we isolated the line migration from the VM and offloaded to the NIC, so that now the line migration data path now look like this. I will do it another time. You can see the round trip does not involve the whole CPU and it's more simplified. Therefore, we remove the overhead on the CPU cores and let the CPU core just run VMs or do hypervisor jobs. How does the SmartNIC maintain data consistency? Say, so on the right, this system architecture figure shows the front end, the line migration module, and the back end. Also, it has access to the network. say a user write falls into a region where the address, the data on the address hasn't been migrated. The user gonna write the data to the source SSD and done. The second case, if the user writes on the region that have already been migrated, there's something more to do. First, the VM write still go to the local SSD, but the line migration module gonna also mirror the write to the destination SSD. If the user writes in the middle part, which is the in-flight part, we're gonna delay and do the double write. Note that we need to maintain strong consistency, and our protocol specifies the LM can only proceed with both writes on the local and remote and be committed. Here's the prototype we built with multiple servers. On each server, within the FPGA SmartNIC, as you can see, we have the yellow part called LM module. We also have other supportive modules for front-end and back-end to access the local SSD and the network. We connect the servers over 100G network. On each server, on the FPGA SmartNIC, our implementation involves 16K lines of system Verilog using Intel Arena 10 FPGA with 100G network, and for Intel 900P SSDs per server. The VMs run either FIO or RocksDB. If you remember this figure I showed in the motivation part, ideally, the line migration is bounded by either the disk bandwidth or the network bandwidth, and the first bar shows the ideal case. The second shaded bar is the configuration where we just do migration without running anything in the VM. With our Pyrocumulus system architecture, for the pure line migration, we accelerated by 1.4 times. And when the host VM is running 100 megabytes per second random read, random write, our approach accelerates by 2.7 times. And when the workload increases to 200 megabytes per second for random read, random write, there could be up to 70 times faster for the entire line migration job. This is due to reduce both the software overheads and consistency overhead with a simplified data path. Another evaluation is on cost. On the host LM, for each disk, minimally, we should use 3 to 6 Xeon cores provisioned for line migration. And different providers have different configurations, but usually for storage optimized VMs, the servers could have 8 to 24 local disks. For Pyrocumulus LM, first of all, as I said, the FPGA SmartNIC is already deployed, so there's zero capital expenditures without adding a new device just for offloaded line migration. And as for the overhead of static provision, we use less than 1% LMs of this particular FPGA. This is a middle-end FPGA. If you use a stronger one, the overhead might be even lower. Or if you use an A6 SmartNIC, the overhead is also lower. We also care a lot about user experience. And we don't want, during line migration time, the user get affected. In terms of the interference, we run RocksDB in the VM, which is widely used by Meta and other hyperscalers. Our finding is that for the 99th percentile latency, we only increase 6.7%. This is mainly because of our offloaded, well-isolated, and hardware-designed line migration. this talk omitted some details, like failure handling, fine-grained lock policy on our double write, and how to handle the network contention between live migration and user network traffic, and also comparing SmartNIC architecture like SoC-based SmartNIC versus FPGA-based SmartNICs. To summarize our work, the problem we solve is that we found storage-optimized VMs cannot support live migration, and we found the challenge is that live migration for this kind of high-performance, I/O-intensive workloads that a user paid off is usually slow and costly. And our solution is using SmartNIC to offload this feature with eliminating the involvement on the host CPU. Thus, there's no interference or minimal interference for the user side. Also, we customize the logic that track consistency and handle the I/Os. The hypervisor level system designs also help a lot in this system. That concludes my talk, and I'll be happy to take questions. Thank you.